current. Current is electricity that moves through a wire.
Yeah.
And the arrow shows the direction of the current. So imagine the current is going up through this wire. Agree? Does that make sense?
Yeah.
Yeah? If I place a magnet near the wire, what do you think is going to happen to the wire?
It's gonna react.
So what happens is, it is going to react, it's going to move, yeah? Any current carrying wire becomes magnetic. Any current carrying wire is magnetic. So any wire that has current in it, even the wire right now next to your computer, if it's got electricity in it, it's got some magnetic character to it. It becomes a magnet or becomes magnetic. And when it becomes magnetic, it means there's invisible lines around it called magnetic field lines. Do you agree with that?
Yeah.
Okay. So if I put a magnet, a real magnet next to this wire, the wire's magnetic, this magnet's magnetic, what do you think it's going to do? It's going to move.
It's gonna move. Like get closer.
Yeah, it might get closer, it might get further, but it's going to move the wire, yeah?
Yeah.
Agree? Okay. Now, this wire, if I want to make it a stronger magnet, the wire can be made into a stronger magnet with three things. Wire can be made into a stronger magnet. How? How can I make this wire into a stronger magnet?
Add some more wire.
Yeah, more wire works. Very good. So basically, more wire, or you turn this wire, you coil it, so you have a lot of wire in one place. Does that make sense?
Yeah.
More wire. The second bit is more current. More current. If there's more current in it, it becomes a stronger magnet. Agree?
Yeah.
And the third bit is, let's say this magnet has this distance here of 2 centimeters. And let's say another magnet has a distance here of 4 centimeters away. Which one's going to push this wire more? The bottom one or the top one?
What do you mean?
So I've got this magnet here near this wire, and the distance is 2 centimeters with this one. But I've got the same magnet, a similar magnet here, and the distance here between the two is 4 centimeters. So which one's going to push the wire more? The one that's closer, is the wire going to feel more force from that? Or is the wire going to feel more force from this one?
Is it the further one?
The closer one. So when you're close to someone and you push them, they feel more force. If I'm far from you and I try and push you, you feel less force. The magnet's just like that. If it's close to you, you'll feel more force from it. Do you get that?
Okay.
Okay. So now let's look at this question. 4 compasses are placed near a wire at points A, B, C, and D. Each wire has a current flowing through it. The direction or the distance of each compass from the wire is shown. What does a magnet do to a compass? If I have a compass here, what does a magnet do to the needle?
The magnet, it points to the compass.
It points to the magnet, it points away. The magnet will move.
The compass points to the magnet.
Okay, so the magnet will move the compass needle, agree?
Yeah.
So imagine I had this wire and I put a compass near it. What's going to happen to the needle? Because the wire is a magnet. Remember we said the wire becomes magnetic. What's it going to do to the needle of the compass?
Would it get closer or do some move?
Yeah, it would move it, exactly. It would move it. Does that make sense so far?
Yeah.
Okay, so now look at this question. Out of all these wires, which one do you think is going to move the compass needle the most? I want you to think about it. Yeah, we're gonna.
One of the 1 centimeter ones, so A or C.
So it could be C, yeah. And why is it C? Because it's not only 1 centimeter, because A is 1 centimeter as well. So C and A are both 1 centimeter. So you're right, the closer one will move it more. But which one?
More it's 4A on C, and on A it's only 2A.
Yes, exactly. So there's more current here. So this is the strongest, it's going to move it the most. Do you get it?
Yeah, I understand.
Excellent, excellent, excellent. So did your dad already explain this to you?
No, he put he marked it.
Okay, cool. So just tell your parents, because you haven't done this with me yet, because you know when you started a few weeks after we'd done this, and that's why you're not you didn't know. It's very easy, and you can see you can get it. Okay, what question should we do next?
Let me see. I'm just looking now.
No problem. Take your time.
I think, I'm not sure it is. It is number 11, I think.
Number 11. Oh, so all the others are right until number 11.
Well,
Wow.
no. It's just I wanted to make sure of it. About
Okay.
it.
Let's
No,
do.
actually, no. I got that right.
Okay.
Um,
You pick. Tell me.
or on page 10, I can't see the question. I think it's question 12.
Question 12. So I'm going to go down the pages, yeah? You can look on my screen as I go down and you can tell me which one to stop on. So page 7, page 8, page 9. Here's page 10, question 12.
Yeah, that's the one.
Okay.
I
So
didn't
you don't understand it, no problem. Let's look at it. A teacher demonstrates static electricity using a Van de Graaff generator. Have you ever seen a Van de Graaff generator in the classroom? Have they shown you this before?
No.
It's basically something you put your hands on, and when you do that, your hair stands up. Have you ever seen that on YouTube or anywhere?
Oh yeah. Oh,
Yeah.
when they put like a balloon on your head.
Yeah, you can put a balloon on your head, but this thing here makes electricity. What it does, it makes electricity. When it makes electricity, it makes static electricity. Do you know what static electricity is?
I know it, but I don't know the exact definition.
Okay, so static means something doesn't move. So when you're static, it means you're not moving. When you have static electricity, it's talking about electricity that stays in one place. Static electricity is basically electrical charge. So you build up electrons, electrical charge. It's like building up rubbish in a dustbin that builds up in one place. Does that make sense so far?
Yeah.
Okay, that builds up. Right, now, a teacher demonstrates static electricity using a Van de Graaff generator. She places 3 metal foil containers on top of the dome of the Van de Graaff generator. When the Van de Graaff generator is turned on, the foil containers fly off the dome one by one. So these containers here fly off. Now, if you look at, let's say, have you looked at the experiment in the lab where they have a rod and they rub it and you can pick up paper with it?
No.
You haven't seen that? Okay, interesting.
No.
Okay, so let me show you a video quickly, yeah, of a Van de Graaff generator in action. Now, this is going to take some learning. So YouTube. Van de Graaff generator and what it does to aluminium. Oopsie daisy. Aluminium. Let's see. Watch what happens here. So this is your generator, yeah? This thing over here. When you put your hand on it, it will make your hair stand up. When they turn it on, what happens? It makes electricity build up here, or charge. And electricity is built up through electrons. You know what electrons are?
I know.
No problems. Electrons are, that's fine. Electrons are just tiny particles, and those particles contain electricity. Clear?
Yeah.
Okay. They're called negative charges. This thing builds up negative charge. Look what happens to look what it's doing to aluminum plates. Can you see that?
Yeah.
It's pushing them off, right?
Yeah, because of the static electricity.
Exactly. It's like if you had a north pole of a magnet here, and these all had north poles, they'd push each other off. Agree?
Yeah.
Okay. So what's happening here is that's what's happening. Now, so when you turn this on, the Van de Graaff generator, this generator thing over here, this thing over here, when you turn it on, there's a belt in there that turns. And the turning belt, it makes what you call electrons build up here. So electrons are going to build up. All these electrons are going to build up. Now I'm going to draw the electrons deeper. 1 second. So electrons are building up. These are all negative charges. Now, when you have plates or aluminium cups on top, what's going to happen? The electrons are going to build up on these as well. These already have electrons. So when the electrons from here and the electrons from here meet, what are they going to do? They're going to push each other. They're going to repel. And when they repel, this will fly off. Does that make sense?
Yeah.
So it's something called charge. When electrons build up, you call it charge build up. In other words,
how should I explain it?
We're gonna come to that. Yeah, we're gonna come to that. Good question. So in other words, when charge builds up, we have static electricity. So charge builds up here. There's a charge over here of electrons, and then they push each other. If we look at your mark scheme, we can see how to explain it now. Let's go to question number 12. 12, 12, 12, 12, 12. Right. So look at this answer here. It says charge is transferred from the dome to the container. So what happens? The charge builds up here, and then the containers get it too. It transfers it over. So there's negatives here, and there's negative electrons there. Then the next bit says charge is distributed evenly across the dome of the containers. They're conductors. What that means is, let's say I'm buttering bread and I put jam on it. I don't put too much jam in the middle of the bread. I spread the jam out evenly across the bread. Do you agree with that?
Yeah.
So the charge spreads out evenly across the dome, and it spreads out evenly across the containers.
Okay.
Like charges, it says idea that like charges repel, because the container has the same charge as the dome. They're both of the same charge. Like charges will do something called repel. They push each other away. Charges on the container repel the charges on the one below, on the dome. So these charges and those charges repel each other. Does that make sense?
Yeah.
Yeah. Do you wanna write the answer down in your own words?
Yeah.
Okay.
So, all of that.
Yeah, all of that, but summarize it in your own words if you want. Yeah. Can you do that? Is that okay, Marco?
Yeah. So.
Okay. Cool. So were your parents a bit upset that you didn't get them all right?
Yeah.
Okay. Just tell them you haven't done it here.
Okay. Thank you.
Then no problems. Hello, Ahima. Hi, Ahima. Can you hear me?
Yeah.
How you doing today? You good?
Yeah.
Okay. Should we start in 2-3 minutes after you read over last week's notes? Are you okay with that?
Yeah.
Okay.
I've done it.
You done it, Marco? Okay. So while Ahima reads her notes for the next few minutes and tells us when she's ready, me and you, we're going to go to the next one. So do you understand the answer to this now?
Yes, like the charges are the same in both
Yes,
the containers and the dome.
yes.
So when the charges are the same, so they move away from each other.
They'll cause the objects to repel, yes. And the charges build up on the dome because when you switch this machine on, the charge will
Yeah.
build up. Yeah?
Yeah.
Okay. So good. What's your next question, Marco? Which number?
Just looking now.
No probs.
I think it's the student removes a material number on page 11.
Page 11. Let's go to page 11. While Sarah, can you see all right?
Yeah.
Yes, yes, sir. Yes, so do me a favor. Just read through your notes and we're going to start, yeah?
Okay.
Okay. So Marco, should we continue after the lesson because we're about to start lesson now?
Yeah, sure.
Okay. And if you want a one-to-one on this where I take you through it, just let me know. I can take you through the whole thing.
No, there's only one other question.
Okay, cool. We'll do it. And just tell your parents not to worry. It's something we will cover. And we just haven't done it yet. Otherwise, you'd have answered it right.
Yeah.
So, okay. Let me just see how Ahim is doing. Ahim, have you read through it?
Yeah, I'm almost finished.
Oh, good, good, good. Salik Majid, you okay?
Oh, welcome, Sami. I'm fine.
Good, good to hear from you. We're going to start our lesson very soon. People are just reading through their notes and recapping last week. Are you okay with that, Adra?
Yeah.
Okay, so we're just going to read through our notes. Let me know when you're done, and I'll open up the lesson. Mark, after this lesson, we'll do the last question together, yeah?
Okay.
Okay, so if you open up your notes from last week and read through it, we're going to start working in a second. Okay, so let me know when any of you guys are finished reading, and we'll start. How's your week been, Yasser?
Good.
Good, good, good. So again, I promised you guys videos. My computer's been playing up. That's the only reason the videos haven't come. Not to worry, because I've got them all, and they will be coming. It must be getting tiring to hear every week they're coming. But it's just a computer issue. Let me know as soon as any of you guys have finished reading. Da-da-da. Are you reading through your notes?
Yeah, I'm done.
Good, you're done? Okay. So we will start, guys, because some of you are done. Some of you probably read through most of it. It's not essential to read through all of it, but what I want you to do is just get a general remembrance of what we done last week so that your brain's ready and primed for what we're going to do this week. It's like warming up for a race before starting one. Get the body ready, get the mind ready. Okay, so what have we been doing over the last few weeks? We've been doing waves, okay? And again, every lesson is recorded, even though they're being sent a bit later than I'd like to. This one is no exception, it's been recorded too. Waves is a topic where we're dealing with the movement of energy. And energy can move in air, in liquids, and in solids. How does energy move in these things? Well, waves is one way in which energy moves through things, okay? Now, what type of waves are there? So like there's males and females in the human family, there's longitudinal waves and transverse waves in the wave family. So energy can move in two ways through waves. It can move in a transverse way, or it can move in a longitudinal way. So transverse and longitudinal waves are two different types of waves. Now, we discussed the difference between them a few weeks ago. We will discuss the difference between them again when I recap this lesson later, or when we do exam questions. So don't worry if you missed that. What we did discuss together was looking at a transverse wave and explaining what it looks like. So a transverse wave is a wave basically where you have something that looks like a wave on a beach, something that goes up and down in very rudimentary terms, okay? Amplitude is how high the wave is, above the middle line, okay? Or below the middle line. It's the point from the middle to the highest point, or sorry, the distance from the middle to the highest point, or the distance from the middle to the lowest point. This is called the amplitude. We should also understand that amplitude is a measure of energy, meaning the more energy you have, the higher your wave is going to be. So if you're in the ocean, the higher the wave is, the more you're going to feel violence from the water, because the water has more energy. So the height of a wave tells you its energy. The wavelength, how far apart the waves are. Imagine you're in the ocean and suddenly you go up. And then it takes so you're in the ocean, nice flat ocean, and there's a wave. Suddenly you go up, woof. And then it might take some time till the next wave comes, and then you go up again. The distance between the first wave and the next wave, the 2 points, is called your wavelength. So the distance between two corresponding points in a wave, as we said last week, is the wavelength. A crest and a crest, a trough or the bottom and another trough. Those two distances are called wavelengths, and many other corresponding distances. Frequency is how many waves pass a point every second. So how many entire wavelengths are moving past something every second? That's your frequency. Imagine a queue. If the queue moves faster, more people get through it every second. If the queue moves slower, being at a low frequency, less people move through it every second. In waves, we're not looking at the movement of people, we're looking at the movement of wavelengths. So just imagine a wave as a queue of wavelengths, one after the other. Frequency equals 1 over period. So frequency, if you want the formula for it, one way of finding this formula is dividing 1 by the period. What is the period? The period is the time taken for one entire wavelength, okay? Usually we can find the period on the x-axis, on the horizontal line here. It will usually tell you what the period is. In these two pictures, you can't see any numbers telling you how long the period is. In exam questions, there'll be numbers here. Let me give you an example. So I'm gonna skip through quickly. Look at this as an example. You can see here on the x-axis, they have t, dash ms. So that means they're measuring time here. In what unit? In milliseconds. Anytime you have something with a dash and something else after it, the thing that comes after is called your unit. It's what unit you're measuring something in. The thing that comes before the dash is called, the thing that comes after is your prefix. So it's your milliseconds or your microseconds or your megaseconds. The thing that comes before is the unit, or what you're actually measuring things in. So here we have time. So we're measuring things in terms of time. If you had a big M here, this would mean meters, and so on and so forth. Let me not confuse you with too much of that. Right. So notice one thing, frequency equals 1 over period. That's one equation for frequency. But also the wave equation talks about frequency in a different way. Frequency is the speed of a wave divided by wavelength. So you've got to remember that frequency can be worked out in two ways. This equation or using the other equation we just looked at. Why is that important? Because a lot of questions that you get, you can simply work out frequency and other things using this situation here. But to use this situation here, to work out frequency in this situation, you need to know the other two. Sometimes you don't know the other two. Sometimes they just tell you the period, how long a wave is, or how long a wave takes. And if you just know the period, in other words, if you look at this equation we looked at, where's it gone? If you just know the period, then basically you can divide it into 1, as you can see from this equation. And when you do that, you find frequency. So remember, there's 2 equations for frequency. You can use this one, or you can use 1 over t. Now, when you use 1 over t, you might get a question like this where you use it. Look at this question, just to recap with you guys. What type of wave is this? You already know. When you look at it, it's a wave that looks like there's a wave on the beach. It's going to be transverse. Amplitude, you know, it's going to be the height. And the height is measured on this axis here, your y-axis. Time period, you already know, it's going to be the time taken to get from one corresponding point to another, meaning, let's say my arrow's over here. Where's the next corresponding point? Going up, going down into the ground, going down right to the bottom, coming up out of the ground here again. So this point here clearly shows you coming out of the ground. This point here as well, you're coming out of the ground. So these are two corresponding points. This one over here where I'm circling now, and this one over here where I'm circling now. The time between them is called your time period. Now, because this picture doesn't tell us anything about the speed of the wave, this V over here shouldn't be confused with speed. The y-axis, the V can also mean voltage. So don't let that confuse you and let you think it means speed. It doesn't, yeah? This axis here, this y-axis, will never tell you speed. So even if they put a big fat V over there, you should know, because this axis over here will never tell me speed, this can't be speed. Therefore, this equation over here, which uses speed, we can't use. So what can we use here to find out our time period? Well, 1 over t. Oh, sorry, to find out our time period, we can just look at it, look, 4 milliseconds. Frequency, 1 over t, 1 over 4 milliseconds. Obviously, if something is in milliseconds, in physics, we want to convert it back to seconds. So we'll convert it to seconds and we'll put it in the equation. Now, I'm going to carry on recapping in a second. Just want to make sure all you guys are still with me and understanding. Are we all, oh, Huzaifa's waiting. So are we all okay with that? Let me ask you one by one. Are you clear on that? Can you hear me, Ajay?
Sorry?
I'm just saying, are you clear on that, what we've done so far?
Yeah.
Yeah, okay. Marco, you clear on that?
Yeah.
Good. Ohima, you okay with that?
Yeah.
Good. Yasser?
Yeah.
Okay. Huzaifa, you okay? We're just recapping, yeah?
Yeah.
Okay. How long have you been waiting, Huzaifa?
I went shopping.
Sorry, no, I'm just saying, I thought you were waiting here for long because I wasn't looking at who was trying to enter the room. So I'm apologizing in case you're waiting for too long.
Oh,
Yeah.
that was fine.
Okay, no problem. So there's some experiments to measure the speed of waves, which we won't go into yet. Okay. We also understood, again, I love to recap at the start of a lesson, even if you know it. It's good always to hear it again from somewhere else because your brain registers it. So the wavefront is basically the top of a wave. If I looked at this ocean from the top, if I was in a helicopter, I'd see lines, yeah, going across. And these are called wavefronts. And so the wavefront is a wave looked at from the top. And this wave is coming towards the coast and is going to hit it. As you can see on this diagram here, the wave might be coming towards the coast. If I'm in a helicopter above the wave, I'll just see lines like this coming towards the coast. We know when a wave hits something that's solid, it's going to be reflected. And there's going to be some angles involved there, which we're going to go on to next, okay? Right, so when a wave hits a boundary, a few things can happen. If the boundary is solid, yeah, if you can't get through it, in the case of water, if you hit a rock, it's not going to go through it, it's going to rebound. If the boundary is not solid, if it's like a piece of glass and you have light, yeah, not water, because glass is solid for water, but for light, light can get through glass, which is amazing. So if your boundary or your barrier through which a wave is going is not solid, if you can, oh sorry, if it's transparent and your wave is light, what will happen? 3 things can happen. Your light can go and be reflected, come straight back off it, like a football hitting a wall. It could be refracted by going through it. It could transmit through the glass, and as it does, it bends. Remember, whenever light goes from something that's less dense, like air is not very dense, into something more dense, like glass, it will bend. And that's how your glasses work. When you wear glasses, light goes into something that's more dense than the air outside, and your glasses bend the light so that your eyes don't have to bend it. Our eyes suffer as we get older. They're not as able to bend light. So we need glasses to do it for us because our eyes weaken. And this is what glasses do. It could also be absorbed. Maybe the light gets trapped in there. And we saw an example of that last week as well. Think about even sound. If I put a barrier in front of my mouth like a tissue paper, okay, and I try and talk into it, you can't hear everything I say. You can't hear everything I say because the tissue paper is absorbing some of my sound. Some of the energy from the sound is getting used up in the tissue paper or transferred into the tissue paper. And the same thing can happen with light, okay? Now, also, one important thing we said last week is whenever a wave goes through something that's thicker or thinner, one thing doesn't change. The frequency never changes, but the speed of a wave can change. How fast it's going can change, and its wavelength can change, okay? We looked at reflection. We said, look, when you reflect something, light reflects off an object, reflects back off. And in the future, I'm going to ask you guys if you'd like me to go through these recaps, because you might be getting bored. Let me know. Let me know in the future. Okay, so there's something called a normal. The objects that you have off of which you're reflecting a wave. If you draw a line at 90 degrees to it, it's called a normal line. Look, this is a straight line here. The only way I can draw a 90-degree line is one going straight up. And then you aim light. There's an angle between this normal line and the light. The light coming in is called the incident ray. So the angle over here, the first one, is going to be called your angle of incidence. Okay. The reflected ray, the light coming back off of the glass, or whatever it is going to be called your angle of reflection. The angle is, yeah? So the angle for the reflected ray, angle of reflection. Always know that when you're reflecting light or a wave, the angle of incidence and the angle of reflection are equal. Snooker players use this. When I'm playing snooker, if I hit the ball onto the snooker table, I pretty much know if the ball's going to hit the table at an angle, it's going to come off at the same angle, for those of you who play snooker. And I can use that to plan my shots. For those of you who don't worry. Okay. Now, sound waves and ears. We skipped the ears part last week, and we said we're going to return to it. That promised will be kept, but we're just going to make sure we get all of the other things about what we call electromagnetic waves first. Now, electromagnetic waves, we said, are those waves that travel at the speed of light. They're a family of waves that travel at the speed of light. And we're going to come to that next. You can see all of these interesting things or interesting stuff we're going through right now. We've skipped that. We will come back to it. I'm just going to skip on. So wave is a movement, electromagnetic radiation, yeah? So electromagnetic waves are waves that travel at the speed of light. There's many types of waves that travel at the speed of light, including light itself. Visible light, the light that you can see, travels at the speed of light. Infrared, the heat from the sun, travels at the speed of light. X-rays, through which you can look at the body, travel at the speed of light. Ultraviolet light, which you might use on a tanning bed, which comes out of the sun, can cause cancer, travels at the speed of light. So many travel at the speed of light. So we got to this point last week. The electromagnetic spectrum is a continuous spectrum. What that means, in other words, it's a family of waves of different wavelength and frequency. They all have different wavelengths and frequency, but they all travel at the speed of light. What are the waves involved? Gamma rays are part of the electromagnetic spectrum. X-rays are part of it. UV, all of these that we can see here are part of it. I think we got to this slide, and I'm going to ask Ajr. So I asked different students, today I'll ask Ajr. Where were we, Ajr, last week? Did we do this page?
No.
Okay, so I believe we've got to this page. What I want you guys to do is basically copy this title down and attempt to fill in the blanks as your starter task, okay? Through that, we're going to learn about it and we're going to move on. All right, guys, let's go for it. Well done. As soon as any of you are done, please tell me. Okay. And then we can discuss further. Perfect. So Josefa, you want to do some A-level biology, your dad's saying, yeah? Can you hear me, Josefa?
Yeah.
Cool. So I want to see if I can find a few students who also want to do it. And if I do, we'll start a biology class early this year. And then by the time September comes, you will have done A-level biology more or less. If there's anyone else from you GCSE guys who want to start learning about A-level biology, let me know, because I might be starting the class. Obviously, some of you are busy and it's a bit early for you. You don't have to. What else are you doing, Josefa, in your A-levels? You're doing biology, economics, and business, is it?
No, maths and psychology.
Math and psychology. Okay. So I'm probably going to start some A-level maths and biology lesson at some point, and I'll invite you to it. In the meantime, just let your friends know so that they're ready, and then if they want to come, they can come too. Okay.
Yeah.
Good man. Anyone, if you finish, let me know as soon as you do. Don't be shy. Don't be afraid if you can't answer them. Don't worry. We're just guessing now for a little while. Then we're going to learn. Marco, how far are you? Whereabouts are you?
Like towards the end, like
Very
on the
good.
second last one.
Perfect. Let me know when you're finished. Cool.
Okay.
Yeah, so anything interesting this week in your life? Yes, sir.
I wait for someone else. Yeah.
Marco, what have you been doing interesting this week, Yasser?
Went to the park for a walk.
Okay, what, Springfield Park?
Yeah.
That's the best park in London, I think. It's a great park in summer. Yeah. Did you go with your family or did you go alone?
Went with my
Okay, nice.
I'm finished.
Excellent, Marco. So I want to start going through it slowly, okay? Now, look at this. These are all called electromagnetic waves. If anyone ever asks you in the future, what is an electromagnetic wave? It's a wave that is part of a family that all travel at the speed of light. And then if they ask you to name them, bang, these 1, 2, 3, 4, 5, 6, 7, the most important ones. So each of these types, I'm going to ask you guys one by one what your answers are actually. Each of these types travels at the same speed through what's that answer there going to be, Marco? Any idea? Huzaifa, any idea? Huzaifa?
Yeah.
Yeah? What's the first answer? What do you think?
Vacuum.
Vacuum, okay? What's a vacuum? It's a place with no air. Now, just remember this. You think, how would I know this? Remember what we learned last week. I'm just going to minimize this for a second, yeah? We learned last week the following. Let me open up my, oops. If my computer suddenly, if the connection suddenly goes, it's because my computer's being a bit funny, so don't worry. It shouldn't go, but sometimes it happens. Okay, don't worry about it. Let me just get this battery in. Okay, if we look at what we learned last week, we learned the following. Let me get it up for you. We said, look, and you guys will agree with this because you'll remember, we said when you have a glass block, yeah, let's say I've got a block of glass here, and light is going into it, and it comes back out. What's never gonna change for this light? Frequency never changes. I'm just doing it really roughly. Frequency never changes. Two things can change. The speed can change, and the wavelength can change. So whenever light travels through something that's denser than air, this is denser than air, denser, and this is air. Whenever light travels through something, its speed will be affected. Imagine you've gone, now you've got air, let's say. Let's say instead of a glass block, you have outer space and the earth. In outer space, let's say you've got the earth here. You've got the earth's atmosphere around it. So this is, let me just draw this out. You've got the earth. You've got the clouds and everything else around here. Let's just draw this, scratch this as the atmosphere of the earth. So when you're looking at the sky, you're on the earth, let's say that's you. You're looking at the sky, you're going to see the clouds. Beyond the clouds, you've got the sun somewhere releasing its waves, and you've got space. And space is a vacuum. And a vacuum is where there's no air. No air. So quick question. Is it going to be thicker here, or is it going to be thicker over here? Ahima, you tell me. Is space going to be thicker for light to get through, or is this atmosphere with air going to be thicker? What do you think, Ahima? Can you hear me, Ahima? Ahima? Okay, no problem. What's going to be thicker is the air. And because this is thicker, when light goes from something thin, the vacuum is thin, into something thick, it slows down. But in a vacuum, light won't slow down. There's nothing to slow it down. There's nothing in its way. There's no molecules here. No molecules or no atoms in a vacuum. That's what a vacuum is. It's a place with no molecules, atoms, empty space. When light goes through a vacuum, it will always have a speed of 300 million meters per second. As it goes into the atmosphere, what will happen? It will slow down a little bit. It might only be 299 million meters per second. This is an exaggeration. Just giving you an example. So whenever light goes from something thinner into something thicker, it slows down. There's nothing thinner than a vacuum. The vacuum is the thinnest thing you can get because there's nothing in it. Yeah, there's nothing to make it thick. So therefore, light will be traveling at the highest speed in a vacuum. So let's look at this. So each of these types travel at the same speed through a vacuum, 300 million meters per second. And different wavelengths are absorbed by different surfaces. If you go out on a hot day and you wear something black, you're going to feel warmer than if you wear something white. Why? Because a black surface absorbs infrared very well. It absorbs heat. So infrared is absorbed very well by black surfaces. This absorption may heat the material up. If I go outside wearing a black jacket, as some kids do, I mean, I go outside, I see some kids in hoodies in this heat. I don't understand. Yeah. If I go outside wearing a black jacket, it's going to heat up. Okay. And what's going to happen then? I'm going to sweat. So this absorption may heat the material up, like infrared and microwaves. Microwaves, you might not have got that. What microwaves do, when they heat your food up, your food absorbs the microwaves, just like a black jacket absorbs heat. Your food absorbs microwaves, and then it gets energy and heats up. So this bit here is microwaves. Or cause an alternating current, like in a TV aerial. So this is an interesting one, and I'll talk a little bit more about it. Back in the day, if you had a TV, back in your parents' day, what you'd find, your TV has something called an aerial on it, an aerial, yeah? A bit of metal sticking out. And if you'd find aerial, there's different ways of spelling it. You'd find if you had no aerial, you'd get no signal. You'd see nothing on your TV. Today it's Wi-Fi. Back in the day, instead of having a Wi-Fi receiver, you'd have an aerial. Why would this aerial make your TV image come along? Because from the TV station somewhere, they send waves to your TV. They send waves called radio waves. And those radio waves, we know, they carry something called information. The aerial picks up this information. It takes these radio waves. Your TV doesn't understand radio waves. Your TV understands electricity though, and it turns them into electricity. And electricity, another word for electricity, is called an alternating current. Electricity, and one way of describing it is called AC, or alternating current. So what waves can do when they hit an aerial, they can create electricity or an electrical current, an alternating current, and therefore waves can be converted into electricity by an aerial. So here, what they're saying is that if you have a radio wave, yeah, what the radio wave can do, it can cause an alternating current. So absorption, when something absorbs waves, if it's a black jacket and it absorbs heat, it's going to heat up the material, okay? Or if it's an aerial and it absorbs a radio wave, it will create an alternating current, like in a TV aerial. Our eyes can only detect a very small part of the spectrum called the visible light region. So in the spectrum, there's all these waves. Some of them we can see. The ones we can see are called visible light waves. So we can see blue light, yellow light, green light, orange light, and so on and so forth. But the ones we can't see, we can't detect, okay? I'm gonna show you guys a very interesting video in a minute to prove something about waves. But before I carry on, I want you guys also to write all of these waves down. And on the left, they're high frequency, low wavelength. These waves, as you go more towards the left here, you're gonna have a very high frequency, but a very low wavelength, very close together. Low wavelength means very small distance, the waves are apart. As you go to the right and go to TV and radio waves, you'll have a high wavelength. The waves are very far apart, but a low frequency. Yeah, there's not many waves passing a point in 1 second. So what do I mean by that? If I look at two waves, let me example you. Well, I'll give you an example. For example, you bad use of English there. All right, make an example of you. Right, so if I look at a big, long, thick wave, and I look at a wave like this, obviously this one has a longer wavelength, big wavelength. But the bigger you are, the less of you is going to move past something every second. So if I have this point over here, let's say these waves are going past this point. This is the point I have, this area, this line. Because the waves are so long, less of them are going to get past every second. So the frequency is going to be low. When your wavelength is longer, your frequency is lower usually. What about this now? There's a lot of waves. The wavelength is small, so small wavelength. But because it's small and it's moving, a lot of these are going to get past this point every second. So small wavelength is usually high frequency, okay? And that's what they're saying here. They're saying in electromagnetic spectrum, as you go from left to right, this is in order, by the way, it's in a special order, the higher frequency waves are here, which also have a lower wavelength, and the lower frequency waves are here, which have a higher wavelength. So I want you guys, if you haven't copied this, to make sure you list these in order and put this little spectrum thing here, put this little informational bit here, talking about high frequency, low wavelength on this side, low frequency, high wavelength on this side. Okay, I'm going to ask you one by one if you've copied it yet, and then we're going to carry on. Mark, have you copied this part yet?
Yeah.
Oh, you have, excellent. Okay, Yasser, done?
Yeah.
Okay, Jose, are you okay with that?
Yeah.
Okay, Ajay, done? Are you okay?
Yeah.
Excellent. And Ahima, you okay? Ahima, can you actually hear me? Yeah? Okay, excellent, excellent, good. So there's all 6 of you have asked, and all 6 of you have agreed. Let's move on, and you're all okay with filling in the blanks. If there's any questions on that, let me know. I will explain to you again. So we know a few things happen when a wave hits the boundary: reflected, refracted, or transmitted. It can go through, meaning transmission, but when it goes through, it bends because it's going from something thinner, usually, into something thicker, okay? And it could be absorbed. It might get stuck in there, and the energy might be absorbed. Just like when you wear a jacket, it absorbs the heat. Okay. Now, this can happen to an electromagnetic wave, yeah? When you have an electromagnetic wave, like light, radio, X-ray, whatever it is, all of these things can happen to those as well. But what does it mean? So let's look. Refraction we've looked at. Now, we've spoken about this. We've spoken about this a little bit as well. Now we're going to add a bit more information here. If I've already talked about this last week, please do remind me. If I haven't, then you can copy this, yeah? So when you have a glass block, we know when light goes in it, it will bend. But which way will it bend? Here's the normal line. So the light's going to go in it. It's going to bend. Look at the way it's bending. It doesn't bend away from the normal. It bends towards the normal. And it goes down and it comes out again. Notice wherever there's an intersection, there's a normal line. So here, look, there's the black space around the glass. We call that air. Here's the glass itself. Between there and the glass, you've got the normal line. Where have I drawn the normal line? Right where the wave hits the block. And I draw a straight line. And that allows me to measure some angles. This bends towards the line here, and it goes back out. Again, this is where the intersection is. This is where the light hits the block and comes back out. Light hits the block and comes in at the top. Light hits the block and comes out at the bottom. So I draw another line here. Wherever there's an intersection, I draw a line. The interesting thing over here is this. This angle here between the normal and the refracted or the bent ray is going to be equal to this angle here. Okay? So what we're going to do, we're going to write about this a bit. And notice also, when the light goes straight through along the normal, yeah, it's not at an angle to the normal, it will not bend, it will pass straight through. So light slows down and bends towards the normal due to entering a more dense medium. Light speeds up and bends away from the normal due to entering a less dense medium. In this one, light slows down because you're going from lighter into heavier, but it's not bent because of the angle you've come in at. So what I'm going to do, we're going to copy this down unless you've already done it last week. Have a go, copy this diagram down, it's very important, and then we'll move on. If you've done it, tell me straight away.
Done.
Done? Okay. So I think we did copy this last week. Do you guys agree? Okay. If you haven't copied it last week, then tell me, and then we'll keep this page. But I think we have done it. It's just them repeating it, and I'm repeating it as well. Okay, so let me check what time break is. We've got 15 minutes roughly for break still. Okay, now using wavefronts to show refraction. And so remember what we said earlier. If we go way back in the day to where we were last week, we said if we look at a wave from the top, we can call it a wavefront. Let's go back to where we were and show you. Where is that thing? Yeah. So if you look at a wave from the top, you see straight lines, and then you can represent it on a diagram as banging into something or hitting something and rebounding off. We used wavefronts here to show reflection. We can also use a top view to show refraction. And this is what you'll do at the higher paper, which all of you are doing. And this is why on the PowerPoint they say higher tier only. So let me go back to it. You'll see this in A-level physics. You'll see this in A-level maths as well sometimes, I think. Especially if you're doing mechanics. I think you'll see it in there maybe. Right, let's go back to it. So imagine looking at a wave from the top. All of the amplitudes are represented using these lines, yeah? As the wave hits a piece of glass or whatever it is, it's gonna bend. It might reflect off, yeah? It might bend in and bend back out. And it might be absorbed. Some of it might go in there and not come out at all. We can use wavefronts to represent this, okay? For now, you just need to understand that. You don't need to copy that. Just remember it, try and remember it. We'll do exam questions through which you can apply it. Okay, so refraction. We know waves can be refracted. We talked about all of that. And here are our wavefronts. So when this wave is refracted, it slows down. The frequency never changes. Don't forget, that's one of the recurring themes in this lesson. One of the things that are constant about these waves, one of the things that never changes, just like you're never going to change from a man to a woman or a woman to a man, hopefully. Yeah. The one thing that doesn't change about waves is the fact that the frequency is always the same. It's their identity, it's their gender, it's something that doesn't change. Okay, right, now, last week we looked at this. We talked about this as well, if you guys remember. Radio waves are sent and they are received. When they're received by a radio, it turns the wave back into electricity, and the radio, you can listen to it. We copied this, if I remember correctly. If we didn't, remind me, but I think we did. Okay, places radiation can come from. This is what we're doing next, yeah? Now, radiation, look at the word radiation. Look at the first part of it. A lot of science and a lot of the things we do in this world, we can have clues about it and understand it from looking at the words themselves. Radiation, radio, yeah? Something to do with radio, okay? And radio waves, or waves, are part of the electromagnetic spectrum. So don't get too hung up on that for now. Let's carry on. So here are two sources of radiation. Radiation is basically waves that are released. The sun releases radiation. Light is a form of radiation. Radiation is another word for waves. And also the atom, if you look at atoms, there's some atoms called radioactive atoms. Radioactive atoms are those atoms which release radiation or a special type of wave. It's known as a gamma wave. Okay, so some atoms, if you look at the atom as a nucleus and electrons, they can release something called radiation from inside the nucleus. And some of you have learned about this already. Okay, so let's actually write something down on this. It's important. I'm gonna open up my notes because the PowerPoint doesn't do a good job of it right now. So radiation, write the little title down. This is a term given to waves which emanate or which come out. Emanate is another word for come out. So I'm going to use more technical language as we go along. This is a term given to waves which emanate from any particular source. From any particular source. Okay. Now, I'm going to make sure my screen is being shared, isn't it? Yes, it is. Okay. So, for example, so you can see my right here, I'm writing, for example, the sun, what does it release? It releases UV. It releases infrared. So the sun emanates many types of waves, infrared or heat. The sun also releases, because we can see it, visible light. The sun is a factory of waves, visible light. Example 1. Example 2, atoms. Yeah, atoms or radioactive atoms release gamma rays. They release a type of wave called gamma rays. Gamma rays, yeah? So these are examples of radiation. And we already know, because we've been awake for the last 15 years, hopefully, we already know that UV, for example, is dangerous, yeah? Gamma rays also can be dangerous. They can kill you. If you get too much UV on your body, it can cause your cells to become cancerous. And then when you get cancer, there's a problem there, obviously. So we also know that visible light doesn't harm you. Yeah, so let's put that in blue. I mean, we're just talking about it now a little bit. Visible light, you need it to see things. Visible light grows plants, so it's beneficial. But also at the same time, UV can be beneficial. How can UV be beneficial? Does anyone know how UV can be good for you? Or good for the world? You can use it in hospitals to kill germs. So doctors, when they do an operation, when the knife, after the operation's got blood on it and germs on it, they'll put it in a machine which shines UV light on the knife. It kills germs. Yeah? Why does it kill germs? Because it's got a lot of energy. It's got huge amounts of energy and it can kill germs. Gamma rays, even though gamma rays can cause cancer by hitting your cells, if you hit cancer cells with it, it can kill cancer cells. So gamma rays are used in chemotherapy, in cancer treatment. So many of these waves, they're a double-edged sword. The term double-edged sword is used in English to describe something which can have benefits and it can also have harms. A double-edged sword, you can kill your enemy with it, but the other edge, you can also hurt yourself with it. In the same way, UV light, you can do good things with it, you can do bad things with it. So make a note of that. I think you already have. If you haven't, tell me, I'll leave it on. Just the things in black, basically. Extra stuff as explanation. Now the extra stuff we're going to get through here. So waves can be harmful or beneficial. In a nuclear factory, in a nuclear power plant where they're using atoms to make energy, the atoms will release gamma rays and different types of radiation, and they can damage you. So you need to wear something called a dosimeter, yeah, which shows you how much radiation you're getting. If you're getting too much, you need to stop working for a little while. Here is a radiation card, and okay, or another type of dosimeter. You can measure how much radiation someone is receiving, depending on where they work, by looking at the number here. This number is a unit, it's called sieverts. That tells you how much radiation you're getting. Okay, it's like kilos and grams. 1,000 grams is 1 kilo. 1,000 millisievert is 1 sievert. Okay, you're gonna write this down in a second. There are 3 types of radiation that can cause harm on the spectrum. Gamma radiation, it can cause cancer, but as we just said, it can cause benefits as well. X-rays, we didn't talk about that, but too much X-rays can kill you. And ultraviolet, it can cause a few problems. I want you guys to copy this page and make notes of everything here, please, yeah? You don't need to write people like me. You can just say radiation dose can be measured using a dosimeter. Then copy the thing in red down, and then copy these 3 points at the bottom. Go for it, guys. And then once you're done, tell me. As soon as you're done, let me know. Which sentence are you on, Yasser?
I'm on the last one.
Lovely, Yasser. Tell me when you're done. Yasser, yes, finished. Good. Okay, no problems. Marco, finished?
I'm about to finish.
About to finish? Okay. Ohima, done?
I'm almost finished.
Lovely. Adra, done?
Yeah.
Okay, good. Jose, you okay?
Yeah.
Excellent. All right, so this will pop up radiation and chemotherapy, and the effects of radiation, I think, can pop up in biology at A-level as well, so it might be useful there. So it's good. All right. And cancer treatment definitely pops up. I think they go into a bit more detail in GCSE, which we'll probably get to soon. Okay, so I'm going to move on unless someone says they're not done. And if you're not done, just you can raise your hand. You can tell me directly on the mic. It's all good. Don't be shy, guys. Let's move on. Okay. So UV, ultraviolet radiation. Ultraviolet radiation, I've never really experienced the bad side of it. And lucky, thank God, because if you're from the eastern part of the world, you're naturally darker in skin. So if you're, or even from some of the western parts, so if you're from the Caribbean or Africa or the Middle East or India or Pakistan, what you're going to have is naturally darker skin. And that means your skin has something called melatonin in it, and that protects you. If you don't have naturally dark skin, and if your skin lacks melatonin, and if you're pure white, and nothing wrong with being dark or white, it's just different chemical compositions. What happens if you're pure white? The melatonin is not there, so your skin hasn't got protection against UV. So when I go to a beach and I'm lying down and I can enjoy myself in the sun, other people who have lighter skin get burnt and they get sunburned very quickly. The sun actually burns their skin because they haven't got the protective chemicals inside it. And so ultraviolet radiation is one of these things that affects people that are lighter in skin more than it affects people darker in skin. If you're lighter in skin and you go out in the sun a lot, you're more likely to get skin cancer than a person who's darker, because your skin is not ready to handle what's been given to it. Okay, so I don't like these, I didn't put these pictures up, by the way. So we have examples of ultraviolet radiation and we need to protect ourselves against it. So sunglasses help, sunscreen helps, wearing clothes helps, all of these things help to protect you, okay? We'll come to that, that's just a brief note, we'll come to that again later. Okay, now look, let's say you're in a city like London, and London is over here. And let's say as you go north, north, north and drive for 4 or 5 hours, 10 hours, I think, up to Scotland, Scotland has a lot of mountains. But let's say there's a TV station in Scotland and they're broadcasting TV or a signal, and you want to watch that TV in London. Imagine this mountain was a bit taller. That signal couldn't get through the mountain to get to you. So what do they do to get the TV signal to you? The Earth has an atmosphere, and the atmosphere above it is made up of many parts. And one of those parts is called the ionosphere. It's very interesting. So what happens? The radio waves, if they want to get TV signals from Scotland over to you, they can't send them straight to you because this mountain here might be too big. It'll block them. As you know, solid objects will block waves, okay? Unless it's see-through, you're going to block light waves and any other type of electromagnetic wave. So what they'll do, they'll send the radio signals up and bounce it off the atmosphere. That's very interesting. The atmosphere acts like a mirror. If you get the angle right, the atmosphere will actually reflect the wave and send it all the way down here, just like a football rebounding off a wall or a snooker ball rebounding off the snooker table. So some radio waves are refracted and then reflected off the atmosphere and suffer little absorption. So when this radio wave hits the atmosphere, some of it might go through and be transmitted, some of it might be absorbed, okay? Some of it might go through, be transmitted. The atmosphere is usually very thick. You're going from thinner to thicker, it's going to bend it, there's going to be refraction in here, but some of it will also be reflected. So some radio waves are refracted and then reflected off the atmosphere and suffer little absorption. There's not much absorption, so not much of the radio wave will disappear here, and which is useful as they can travel further distances. So they can make a radio wave from Scotland to you by using the atmosphere as a bouncing tool. I want you guys to copy that down, okay? You don't have to have the diagram. You can copy it down. Whilst you copy the sentence, I'm just going to close my door. Okay, I'm back and I've got my headphones on. So I'm going to move to the next slide unless you tell me you need me to wait. Okay, I'm going to move to the next slide in 5 seconds. And don't be shy if you need me to wait. 1, 2, 3, 4, 5. Okay, so this is useful because it can be used for communication or sending signals. Okay, now using the satellite works in a similar way. Sometimes the atmosphere is not the most efficient way. Okay, it works, but it's not the best way to make things work. It works for radio waves very well. What we do in the modern age is basically, imagine this is a person, or imagine this is Netflix somewhere in America, and you're here in London with your mobile phone, and you're trying to watch this movie on Netflix. Netflix sends a signal for the movie, but it doesn't bounce it up the atmosphere. It bounces it in a much more efficient way. It uses a satellite dish. What do satellite dishes do? They're amazing because they can absorb waves. They can take waves in. They can also reflect waves. So this signal is sent to the satellite dish and then it's reflected back to your phone. Now, radio waves, yeah, can be reflected off the atmosphere. Your phone, the Wi-Fi, Netflix, all of that stuff send signals using microwaves. Why microwaves? Because they're better to send information with than radio waves. They're more efficient. And so in the modern day, we use something called microwaves. And microwaves bounce very well off of satellites. And then they get to your phone. Okay? So just know that. It's very important, yeah? You don't have to copy that down, but you can just copy a sentence saying, microwaves are used to communicate with satellites. You don't have to copy the diagram. So that one sentence you can write next. If you want, you can go back to this video later and copy the diagram, not a problem. And I blame my computer for the videos not coming through quickly, but that's another issue. So it's fixed now. Okay, so let's move on. Before I move on, we've got 3 minutes left before break. So using infrared waves. Now, you might have grown up in the last 5-10 years, which you have done, and you might have seen that your remote control on the TV has a little red light at the end of it. That little red light can be used to send information. Just like microwaves can be used to send information, radio waves can be used to send information. Infrared waves can be used to send information as well. We're seeing a pattern now. Waves can carry information. Okay, so remote controls. The signal from the remote contains a set of digital codes that carry different instructions. So when you press a button in your remote, it has an electrical signal, digital codes. That signal then needs to get to your TV. So what the remote does, it turns the signal into infrared light. The light goes across all the way to your TV. Your TV takes the light and gets the information out, which is what channel to change to. Very important. Body heat. So I had one of these in my house, okay? If a burglar walks in, the heat from their body is detected by this detector, your infrared heat. And then the alarm is set off. Very interesting. So guys, I just want you to copy this and then we're gonna go for a break. Copy this down. And then I'm gonna ask you how long you wanna break for. As soon as you copy it, let me know. Using infrared waves. We're looking at the uses of waves now. And which we're looking at the uses. So what did we do? We introduced, while you copy, I'll just talk to you about it. We introduced the electromagnetic spectrum. We said it's made up of a family of waves that travel at the speed of light. We looked at radio wave. We looked at some of the waves in the spectrum and how they work. So we looked at radio waves and what they can be used to do. They can carry information. They can carry information, be picked up by an aerial. That aerial can then turn the wave into electricity, and then you get whatever device you have working with the signal. We looked at we looked at gamma ray. We looked at natural radiation from the sun and from atoms, and how it can be useful and harmful. We looked at microwaves a little bit and how that's transmitted through satellites. We looked at radio waves and how that's transmitted using the atmosphere. And now we're looking at infrared. So we've done a pattern. We looked at what the electromagnetic spectrum was, some of its uses, and now we're going to move into other stuff. So, copied it yet, Zephyr?
Sorry?
Have you copied it yet?
Yeah.
Excellent. Adrian copied?
Yeah.
Excellent. So, Ahima, you copied it?
Yeah.
Excellent. Yasser done? Yasser's
Yeah.
Okay, excellent. And Marco?
What did you say?
Have you copied it, Marco?
Yeah.
Excellent. Okay, so now you guys probably know what the next question is going to be. How long do you want your break for? I'll start with Josefa, and I guess he's going to tell me 20 minutes, but I'll ask anyway, because it's become a tradition now. Josefa, how long do you want to break for? 15, sorry, not 20. How long do you want to break for, Josefa?
15.
Okay, cool. If you guys tell me yes, less, I'll give you less, not a problem. 15 is good for me as well. I don't mind. Ajur?
15.
Excellent. Ahima, how long would you like a break for?
15.
Okay. Marco?
15.
Excellent. And Yasser?
15.
Excellent. Okay, guys. So what it is, it's 5:16 now. It's going to be 5:17. So we'll come back at 5:32. Okay, leave your computers on. Well done. 5:32, we'll be back. Well done. Turd. Break. What do you know? Go back to lesson. Okay. Mhm. 2 more minutes. 1 more minute. Okay. Okay, guys, ready? Let's ask you one by one. Is AP back? Okay, Yasser? Marco? Ohima?
Yeah, but
Excellent, Ohima?
I'm back.
Excellent. And Audrey?
Yeah.
Excellent. Okay, let's get cracking with this. Okay, we looked at the electromagnetic spectrum, some examples of different types of waves that exist in the spectrum, and some of their uses. And we touched upon some advantages and disadvantages. If you remember the double-edged sword principle, for example, some of them are useful, but they can also cause harm. And you have that all in your notes right now. So what we're going to do now, we're going to write down the uses and the dangers. We're going to go more into this double-edged sword sort of thing, where a wave can have benefits and it can have harms. The reason we're doing this is because a lot of exam questions, they give you a 6 marker, or even a less highly marked question, where they want to make sure that you understand what the electromagnetic spectrum involves, all of the waves that you can see on the left there, what their uses are and what their dangers are. The 6 markers make you compare the uses and the dangers and evaluate. But before you can do all of that, you need to actually know what they are. So we're going to draw a table just like this. We're going to write down the uses and we're going to write down the dangers. And I'm going to explain a little bit more about them after you write them down. Okay. So we're writing this to memorize it. That's what we're doing. Okay. Have a write of this, and we'll talk about some of the other things. Tell me as soon as you're finished. So a lot of note taking lately in physics, which is good. Again, as soon as you're done, just let me know. Are you done?
Yeah.
Okay. Let me ask everyone else and see what there are. Marco, how far are we?
Nearly done.
Okay, excellent. Jose, nearly done? Yes, sir. Okay. And Ahima?
Nearly done.
Nearly done. Okay. Let's spend about 10 more seconds or 20 more seconds, guys. And then I'll ask you if I can move on. Okay. So I'm going to move on. Actually, I'm not going to move on. I'm going to talk about it a little bit. It's interesting. It's important to talk about it a little bit. So gamma rays, okay? Gamma rays are these high energy rays, okay? They can be used to treat cancer and sterilization. So if I have a dirty medical instrument, for example, like a scalpel or something that looks like this, what you can see in the camera right now. This one looks a bit weird. I'll explain to you what it is if you ask me later. But basically, if you have something that's been involved in an operation and you have germs on it, you place it in a machine and then you expose it to gamma rays. The gamma rays will then come and kill the cells of any bacteria or anything else that is present on the object. Okay. The problem is when it starts killing cells, when these gamma rays start killing cells, they can do two things. They can damage the cells and not kill them. And this causes something called cell mutation, when you've not killed a cell, but you've damaged parts of it. And mutated cells are cancer cells, and they can come and kill you. At the same time, if you have a mutated cell and you keep on pointing gamma at it, you'll kill the cell. So it can kill cancer, it can cause cancer as well, paradoxically, and it can clean objects. X-rays. We know X-rays are used to look at our bones in the medical industry, but it can also cause cell mutation. So the reason these rays cause cell mutation is because they have a lot of energy. When your cell absorbs that energy, it can start unraveling and it can mess around with your DNA. Ultraviolet, again, high energy, can give you a suntan, which is a benefit because tan skin looks nice. Depends, that could be subjective. Some people don't like it, another story. But it can also give you skin cancer. Visible light, benefits, you can see things. Also, you can use it in something called, and we're going to learn about this shortly, fiber optic cables. Fiber optic cables allow you to communicate and send signals. There's special wires. And visible light can be used to help us use these cables. There's not really many dangers, but if the light's too strong and you look into it, it can blind you temporarily, or it can even damage you, for example, the sun. So there's not really many harms, but very powerful light can cause damage to your eyes. Infrared, you can use it in your remote controls. You can use it to transfer heat. When my heater heats up in the room and my room heats up, infrared's coming out of it and helping me. The problem is sunburn. Again, skin problems like ultraviolet. Microwaves, satellites and phones. Your satellites use microwaves, your mobile phones use microwaves. Not many dangers, although there can be, there are some people who say microwaves can damage you. This is why we have a problem now, big problem with some people and 5G. They're saying 5G network, these 5G aerials can cause damage because they release microwaves and microwaves of energy, and the energy can cause cancer in your body. There's not really much proof that that can happen in real life, but we don't know yet, so we're not sure. An exam board will tell you there's very few dangers, but I'd like you to go through life in the back of your head knowing we don't know enough about it yet. We haven't found anything in science that proves it's dangerous. That's the point. TV and radio waves, okay, can be used in communications, and we've not found any dangers for those either. So very few, or none almost. So, okay. Now that you've written all of that, hopefully, we can move on. I would love to give you a 6-mark question today on it, but I think we'll focus on learning everything, and then we'll go to the questions once and for all. Lenses. Okay, so we talked a little bit about glasses. We also talked about lenses in homeostasis a little bit. What we're going to do is now go into lenses in detail. So the physics of lenses can be boring, but I'd rather you do it with me and learn it so that when you go into it in the future, you won't have problems with it. Okay, so lenses. Let's write this title down, guys, lenses. You already know what lenses do. And usually before I started on lenses, I'd ask you an exam question. But today we're just going to move through it because there's a lot to cover. So how do lenses work? Obviously lenses take in light. Where does the light come from? It comes from around you. What is around you? Air. So lenses take in light from somewhere less dense to somewhere more dense. And when that happens, you know, light will bend. You know, its wavelength might change, its speed might change, but one thing that never changes is its frequency. We've learned all of this. And look at how we're revisiting it. So lenses use the idea of refraction. Light enters a more dense medium, it will slow down and bend towards the normal, as we know. When it goes out of it, it will bend away from the normal, as we know. And we don't need to copy this because you already know this concept. But the next bit is going into something now that we haven't covered in detail yet. A prism. A prism uses this idea to split light. This happens because purple light is refracted more than red light. Look at this. So if you look at white light is like a cocktail. It's a mixture, like a mixture of drinks. It's got all of these different ingredients that make it up. And the ingredients that make up white light are red light, orange light, yellow light, green light, blue light, indigo, purple, violet. There's many colors that make up white light. Now, I want you guys to start thinking about this with me. We're gonna write a little bit down on it in my notes because I think these guys are deplorable sometimes and they don't give enough in the notes. So prisms and white light. Let's write this title down, guys. If you can't see my whiteboard, let me know. So prisms and white light. Ironically, I'm writing it in blue, but that's just a cause of this pen. Okay, so a prism is a lens. A prism is a type of lens. Is a type of lens. It's something that's thicker than air. Light goes through it, it will bend. Does the same thing a lens does. It will bend light. It will bend light. Now, here's an important relationship. I'll write in red. The more that light is bent, the more it is slowed down. The more it is slowed down. Remember, we slow down light when we bend it. The more we bend it, the more we slow it down. The more it slowed down. And here's a key point. Again, because of the importance of this, I'll change the color here. Okay, let's look at this. Here's an important thing. Longer wavelengths. This is very important. Longer wavelengths bend less than shorter wavelengths. This is very important, and we'll look at why this is in a second. Okay. So I want to draw a little prism underneath this. So we said so far, okay, we're looking at prisms and white light. We said a prism is a type of lens. We know it will bend light. We know the more that light is bent, the more it is slowed. We say the more that something bends light, the more the light will slow down, okay? If you're running in a straight line, you're faster. The more someone pushes you to a side, the more you're going to slide down. In the same way, if light is going in a straight line, it's very fast. The more it's bent, the more it's being pushed to a side, the more it's going to slow down. Longer wavelengths bend less than shorter wavelengths. What do we mean by this? Well, let's draw our prism. I'm going to draw a little prism out, and we're going to draw it together. So here's your prism, and I'm going to draw white light. I'm going to represent it using a black line, ironically, yeah, because white on white, white screen, white line won't work. So we put a white line in there. We say, look, this is white light. Yeah. So white. We say this is white light. Now, we know white light is made of many colors. So it's made up of, the easy way to remember, if you remember from school, Roy G. Biv. Roy G. Biv is the way we look at and remember white light. So red, orange, yellow, blue, green, indigo, violet. This is interesting. As you go towards the red bit, as you go this way, your wavelength is getting longer. This is very interesting. Red light has a longer wavelength than blue light. Blue light has a longer wavelength than violet light, and so on and so forth. So longer wavelength. Now you're going to see here the magic of this, because we said the more the light is bent, the more it's slowed. Fair enough. Longer wavelengths bend less. So the red, as you go through this, won't bend a lot. It will bend less. This is the important thing about lenses. What they do, longer wavelengths will bend less. So the red light would bend a little bit. Orange light, let's try and get some orange over here in the house. Orange light will bend more because orange has a shorter wavelength. Look, the longer wavelength. As you go to the left, the wavelength gets longer. As you go to the right, the wavelength is getting shorter. So if I have orange, which has a shorter wavelength, it will bend a bit more. So here's orange. Yellow light is even shorter. So if I have yellow, it will bend even more. So here's yellow. Blue light is even shorter. So blue will bend even more. So the prism separates light because it bends them to different amounts. The prism separates light, separates the components of white light, separates the components of what makes up white light, the components of white light by bending them to different degrees, by bending them to different degrees. Degrees means amount or angle, to different degrees, to different degrees. And why is that? Because the longer wavelengths will bend less. So the longer wavelengths will bend less. We can look at this and use it to explain that. The longer wavelengths like red will bend less. The shorter wavelengths will bend more. And therefore white light, which is made up of different colors, the different parts are bent by a prism to different amounts, because that's what the prism does. It bends things. And this is how you separate white light. Okay, so while you copy that, I'm going to ask you guys, I want to make this bigger so you can see the whole screen. Do you get that, Huzaifa?
Yeah.
Yeah. Okay. Did you know that before?
Not really.
Okay, excellent. So something you've learned hopefully something that occurs in nature and also occurs in glasses and other things that humans make, the bending of light. And we've learned a very important relationship here, that the longer your wavelength is, the more you bend. And the prism takes advantage of that by separating using that principle. Does that make sense, Ahima?
Yeah.
Excellent. And also, Yasser, make sense?
Yeah.
Good. Marco? Marco, you there?
Yeah.
No. Okay, make sense?
Yeah.
Okay. Audrey, you okay with that?
Yeah.
Excellent. So this is the beauty of physics here, because now when you look outside and you see a rainbow, you know the raindrop is just like a prism. It's like a lens. It's thicker than the air around it. So when sunlight passes through a raindrop, what's the raindrop going to do? It's going to separate the light into different colors. And then what you have, that separation of light, you'll see it as a rainbow, because that's exactly what's happening. The rainbow is just the prism effect, and the little prisms of the raindrops are doing that for you. So nature is beautiful, because what happens in the lab is matched by nature. Okay, we'll carry on. Right, so lenses. Now, lenses, so we looked at prisms and how they work, and we've understood the concept now that a lens will bend something, okay? And the thicker it is, the more it will bend something. And this is interesting because the prism uses this. And the way the prism is shaped, it will bend it and separate things out, just like a raindrop or even a teardrop. Sometimes if you're crying, if you have eyes full of tears, they're hopefully tears of happiness, things appear blurry because your tears are refracting and bending the light. This is why tears make your eyes blurry. Okay, so there's two types of lenses in this world. In fact, there's more actually, but we're going to look at two. Converging and diverging lenses. When you converge, it means you bring things together. If I say the crowd is converging in the streets, the other day there was protests in London, crowds were converging. They were coming together. The police then tried to separate them. They tried to diverge them. Lenses do this to light. Just like the police do this to crowds, lenses can bring light rays together and lenses can separate light rays. So converging lens, one that brings light rays together, is the thickest at its center. A diverging lens, we're going to look at in a second, is going to be thin at the center. So it's shaped like two C's back to back. So a converging lens, whether it's looking like the one on the left here or the right here, as you go towards the center, it gets thicker. A diverging lens, as you go towards the center, it gets thinner. So I want you guys to make this point. Write down the title, write down converging lens, what it is, and diverging lens, what it is. Converging is known as convex, conv. Diverging is known as concave, conc. Okay, I'm going to move on in about 5 seconds. If you guys need me to keep it on for longer, let me know. I'm going to count down from 5, 4, 3, 2, and 1. Okay, so you guys are okay that hopefully you can draw the diagram to help you, or even just looking at this information here will help you decide when you look at a lens what is converging and what is diverging. Okay, so what do these lenses do? A converging lens, the name will tell you. Light rays are going into it. We represent light rays using arrows. The converging lens will bend the light rays. Because it's very thick at the center, it bends them towards the center, which is interesting. So look, you see all of these rays bending, 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 bending. As they come out, it bends them and it focuses them, brings them all to one place. And this place is called our focal point. The focal point is where a lens bends all the rays of light to. So we call that the focal point. Now, if you look at the lens and you draw a line down the middle of it, yeah, and you measure the distance from this line to the focal point, to what we just spoke about, we call that the focal length. If you ever become an optician, this length here, you'll be speaking a lot about it. So a converging lens, the rays of light are refracted inwards and meet at something called a focus, or the focal point. Right. This definition here is important. This will form an image. If you have a screen here, your image, your light that's going through will end up on the screen. So the image formed is virtual or real. What does that mean? A real image can be seen on a screen, okay? So this light, if I had a screen here, you'd see the light on the screen. A virtual image cannot. So this is a real image, for example. You'll be able to see it on the screen. What I want you guys to do is copy that first bit down. Draw the diagram as well. Write down focal length as well. Do all of this stuff over here. It's very important. Lots of note taking. Sorry about that, but it's important. So you make sure you draw the diagram, show what it's doing to the rays of light. Label this thing in the middle over here where my arrow is as the focus. This is the focal length. This focus, or this bit that says F in white, can also be called your focal point. Okay. As soon as you've done that, all you can do is move on to what we call a diverging lens. And if you're still copying, you can have a little look while I explain if you want. Light goes in, and you can guess, diverging, crowd splits apart, we said. It spreads the light apart, like a torch. What does a torch do? Torch spreads light out. So you can imagine now that at the end of a torch, you should have a diverging lens to do that. The rays of light are refracted outwards. A virtual image is formed. In other words, the image doesn't actually exist. So what happens here is it makes an image that you won't be able to see an image on screen. If you use a diverging lens, it won't be able to make an image on the screen with it. We'll have more on that later. But for now, we'll just copy it down and get the keywords in. As soon as any of you write it down or finish writing it, let me know. Done, Yasser?
Yeah.
Okay. Marco, done?
Yeah.
Excellent. I'm guessing everyone's done by the answer I've received from you two. So if you're not done, guys, let me know. Or put your hands up on the screen or let me know by the audio and we'll keep it here. Otherwise, we'll move on. We're looking at ray diagrams, diverging and converging lenses and what they're doing. We looked at words like virtual and real, okay? Now this, I'm gonna repeat it once more. A virtual image is one that so real and virtual. Remember virtual reality. The word virtual means something that's not really there, okay? So something real you can see on a screen. A virtual image you can't see because it's not really there. That's one way to remember it. We are gonna do some exam questions on it at some point where we're gonna solidify it, okay? So for now, just understand that the definition is, it means something. Okay, now here, this is very interesting. If you look at what I've just brought up on the bottom diagram, I wanted to bring this up last because I didn't want to confuse you with it initially. So we said there's a focal point here where all the light is focused. But over here in the second one, there's no focal point because the light's going outwards. It's not focused anywhere. What we do here is we make an imaginary focus. So these rays of light that are going outside, look at these rays over here. We draw imaginary lines coming backwards from them. Draw imaginary lines coming backwards from all of them, okay? And these imaginary lines that come backwards, or dotted lines as you'll see, they'll meet somewhere. And that will be called your focus. So you can see here, the focus is behind the lens. Here at the top, the focus is in front of the lens. So just make a note of that. Draw that onto your diagram and say, you can write additionally next to it that the focus is behind the lens if you want. And the focal length, as you know, is the distance from the middle of a lens to where the focus is. This is your focal length. So get that down, guys. And then we'll move on. Okay, I'm going to give you guys 10 more seconds. Five, four, three, two, one. Okay, we have about 10 minutes left. Good to see we're nearly at the end of the electromagnetic part. There is a bit more, and then we have to go back to the ear later as well. So we'll probably do that next week. But let's finish off what we can today. Okay, magnification. Now, I taught recently some students who want to do medicine during university, and magnification came up a lot with them. If any of you are intending to become doctors, this is going to, at some point in your life, you'll come across this. If you're doing GCSE science, you're coming across it now. So everyone gets to have a taste of this one. Magnification. Let's write this down as our title, magnification. When you magnify something, you make something bigger, yeah? You can do that using a lens, right? Now, so basically magnification means I wouldn't write how much bigger the object looks. I'd write increasing the size of an object, yeah? Increasing the image size of an object, maybe. If you write this down, it's not going to hurt you, but me personally, I like to use more scientifically accurate terminology. Okay. Now, what you want to do, there's a formula. So I want you to copy this down. Magnification equals image height over object height. How do we use a formula like this? Well, there's two things when you're magnifying something. You're going to copy that in a minute, actually. If I go over to here, just to explain to you, you can copy that in a minute. You might have, let's say, an object, like a small miniature building. Got a small miniature building, okay? This is your building. Not a great drawing. Now, you have your magnifying glass or something, or you have some type of lens. And so this is your lens or your magnifying glass, some type of lens. What's going to happen here? This is your object over here, object. You might send, so there's going to be rays of light coming out of this object. This is a very rough diagram, by the way, so don't take me to account for it. The rays of light are going to come out of this object. They're going to go into the magnifying glass. And what the magnifying glass does, it makes it look bigger. So it spreads the rays out a bit. And now, you might have a wall here on which you see the image. You might have a screen. And on that screen, your building, or your building, which was in blue here, your object, you'll get an image of it. And the image will be bigger because your magnifying glass makes it bigger. So there's two things involved over here. This object has a height, we'll call it H. This image has a height, we'll call it H. Which one's real? This one's real. This one is actually real life. This is your image. This is not real. And I'm not talking about real or virtual here, I'm just talking about real in general. So this is your image. So the image is what you get as your picture. Magnification. Imagine this was 10 centimeters high. Imagine this was 100 centimeters high. How many times bigger is this than that one? 100 over 10, so equals 10. This is 10 times bigger than that. This is 10 times magnified compared to that. So magnification, we have the height of the object divided by the height of the height of the image. Yeah, this one. Divided by, over here, the height of the actual object. And if the height of the image was 100 and the height of the object was 10, 100 over 10. We've increased the size of the object by 10 times. So you don't need to copy that. That's just a rough explanation of what's going on here. The formula is basically talking about that. So magnification equals the height of the image over the height of the object. Or M equals V over U. V represents the height of the image. U represents the height of the object. And what you can do, you can copy that down. And as a finisher probably, or just before we finish, we can do these questions, okay? I want you guys to copy the formula down, do the questions, and then tell me as soon as you've done it, so we can look at the answers and move on. So as soon as any of you guys are done, just say done. I will go through it. I'm going to go through the answers very, very shortly, but I want to make sure you guys have all done it. So don't be shy to tell me if you've done it. Andrew, which question are you on? Can you hear me, Andrew? Okay. Jose, which question are you on? Josefa?
Sorry?
Which question are you on?
The second one.
Excellent. Marco, which one are you on?
The second one.
Excellent. Ohima, which one are you on?
The second one.
Lovely. And Yasser?
The second one.
Lovely. Okay, I'm going to wait for you guys. Tell me as soon as any of you are done. Audrey, can you hear me? Interesting. Okay. Don't worry about number 3. Don't worry about number 3. Number 3 is not important. Just do number 1 and 2, guys. I'll repeat, just do number 1 and 2 and we'll go through it. Okay, we're going to go through it in about 5 seconds. Andrew, you okay? Okay. So the first answer, I'm getting an answer of 5. So the actual size of the ant is 4 millimeters in this one. So the object height, the ant's the object here, is 4 millimeters. You put it at the bottom. Enlarges it to 20 millimeters. So 20 millimeters is the new size, the image height. So 20 over 4 gives me 5. Okay, that first answer is 5. Just check your answers and make sure you've got it right, guys. The second one, a microscope has 100x magnification, so 100 times. So it makes something 100 times bigger. That's what the X means. If it is used to look at a speck of dust 0.01 millimeters big, how big will it look through the microscope? So now, the object height, the actual height here is 0.01. So we put it down at the bottom here, where U is, or where the bottom is. The magnification is 100. So simply, if we want to find out the image size in the microscope, we just do 100 times 0.01. So I'll get an answer of 1 millimeter. Okay, 1 millimeter. I'm going to ask you guys one by one if you got those answers. Yasser, did you get the answer?
Yeah.
Excellent. Huzaifa?
Yeah.
Okay, Ajay?
Yeah.
Okay, good. Ohima?
Yeah.
Excellent. And Marco?
Yep.
Lovely. Okay. Let's move on from there, guys, because your magnification knowledge is there. And let's check what time it is before we move on. Okay, it's 14 minutes past. We've got 1 minute left. So we will call it a day. Next week, we're just going to look at visible light a bit more. And we are going to go into something we spoke about today, which is different wavelengths and how longer wavelengths are bent less, shorter wavelengths are bent more. Now that you know the knowledge, you're okay with that? when light hits a material, we're going to look at transmission, absorption, and something called specular reflection and diffuse reflection. Some of you will have seen this in year 7. After that, we're going to look at filters, which is, I don't particularly enjoy filters, but we're going to run through that very quickly. We're not going to spend 5 slides on it. We'll run through that quickly. And then we're going to finish off. I'm not going to kill you guys with too much more depression today, although physics is enjoyable. Well done. Okay. So guys, I'm going to let you go, except for Marco, who I want to keep back for a little bit to talk about something. Well done, guys. Call me during the week if you need any help with anything, any homeworks or anything like that. Hima, I believe I see you tomorrow at 3 p.m. Is that correct?
Yeah.
Excellent, Hima. Have a nice day, Hima. Well done. Any questions? Welcome.
No.
Excellent. Have a nice day. Audrey, you okay?
Yeah, thank you.
Welcome. Well done. If there's any questions, just ask. Jose, for you good?
Yeah.
Excellent. Well done. Any questions?
Yeah.
No? Okay. Have a nice day, Josefa. Okay. Yasser, any questions?
No.
Well done, Yasser. You're doing well. Are you learning in these lessons?
Yeah.
Very, very good. I'll see you next week, inshallah. And also, bear with me. The videos are coming. We just had some computer issues, okay?
Okay, thank you.
Okay. Welcome. Are you okay with school? Are you having any difficulties with any homeworks or anything?
No.
No. What are you covering right now in class, in school?
What we just did, path and
Okay, so you must be smashing it. It must be very easy for you.
Yeah.
Okay, give your dad my salams and I'll see you.
Okay, bye.
Bye-bye. Bye. Marco, my friend, let's start doing your physics. Let's finish it off. Cool?
Okay.
Okay, good man. So,
Only one more question.
only one more question? Okay, lovely. So we're gonna get it done and we're gonna make sure you're okay. So did you know this question here with the static electricity, Marco? Did you do the second bit as well, the calculation, part B?
Yeah, well, I got it wrong.
You got it wrong? Should we
But
talk?
I think I know why, because I put 0.2 seconds instead of 0.25. I don't know, I can't remember what it is.
No, you're right. Because look, I'm just going to talk you through this quickly before we do our last question. Yeah, in this question, what they've given you, they've given you a formula, and they said, let me just bring up the screen. Look. So in this question, they've said, calculate how long it would take a charge of 5.0 C. C stands for coulombs, to flow with a current of 25 MA. Small m means milliamps. Yeah. So they've given you a equation, charge equals current times time. So charge flow equals current multiplied by time, right? Now, what have they given you? They've given you the charge, which is 5 equals current. They've given you 25 milliamps. Can we use milliamps or do we need to convert it? We should all, yeah, we have to convert it to amps, yeah?
Yeah.
So there's a little rule I'll write down for you. Milliamps, always convert it to amps. So you always have to convert it when you're doing a question. Is that okay?
Yeah.
And if you want to convert milliamps to amps, you just simply divide by 1,000. So this is something you just have to remember. If you want to go the other way, times by 1,000. Clear?
Yeah.
So 25 milliamps divided by 1,000, it will give you 0.025. So 5 equals, this 5 was your charge, equals 0.025 multiplied by time. Agree?
Yeah.
Now, what would I do next to work out the time?
You would wait. So would you do 5 divided by 0.025?
Beautiful, equals time. Just imagine this is algebra. So imagine time is x. 5 equals 0.025 x. If I want to find out x or time, I divide this side by 0.025, cancels. I divide this side by 0.025, and I'll get my answer. Is that clear?
Yeah.
And I might get something like 400 seconds or whatever it is. But that's how you do that one. You okay with that one?
Yes.
Okay, good. Let's see the last question that you need help with.
It's a 6 marker, I think.
Okay.
Or no, I think I did all right with that. No.
Okay, you tell me when you're ready. Can you hear me, Marco? Your sound is a bit off. Marco?
Hello?
Hello? Yeah, can you hear me?
Hello?
Can you hear me?
Can you hear? I can't hear you.
1 second. 1 second. Can you hear me now?
Hello?
Hello, Marco. Hello? Hello, Marco. How are you? Okay, so let's look at this last question. I don't know what's happened to the mic. Hello. Hello, Marco. Sorry about that. Yeah, I think something just happened with my microphone, but we can explain it on the phone, yeah? Are you okay with that? Okay, so if you look at your screen, let's scroll down to which question it was. So what question's next? Which question is it that we need help with? Okay, let's check this out. Number 13 on page 13. Page 13. Oh, this one here. Okay, Fleming's left-hand rule. So this is a long topic. What we'll do, I'll try and explain it to you now. So, have you studied Fleming's left-hand rule before? All right. I'll explain it to you. 1 second. So if you haven't done it, how come they're asking you questions on it? Random. Aha. All right. So this one, basically, this is a long topic, yeah? So it's going to take a while to explain. Okay. Yeah, up to you. Do you want to do it on Monday? Because if you tell it, I don't mind. Is it because you're tired? No problem. No problem. Okay, so just tell your mom because you were tired, you wanted to do it on Monday. Is that okay? All right. So I'm happy to do it any day you want. So because you're tired, it's only one question. We'll finish it off on Monday, yeah? All right. Don't worry. You're going to get it. It's going to be easy after I explain it to you. Have a nice day, Marco. See you later. Bye. Bye.